So here we go. We ready? I don't know if I am, but we're gonna try. We're gonna talk about the particle nature of light today, and we're not even gonna get to like the real particle nature. I don't know. We might. We'll see. We'll see what happens.
It's like a new lesson.
Yeah. Well, it's the same unit, but it's the next part of that same unit. So a new lesson. Yes, it's a lesson within the unit. This unit is really long.
What's it called again? The particle nature of light.
Particle nature of light. So I just want to kind of recap what we did in those last, because it feels like it was a long time ago since we had a long weekend. And then you guys begged me to do these labs yesterday. So we talked about the wave nature of light. Remember we talked about the electromagnetic spectrum and how the visible is a very small portion of it. And we talked about how low energy waves are like communication waves, and then the high energy waves are the gamma rays. And then we did some labeling of a wave, where you have a wavelength is the length of a wave, and the frequency is how many waves pass in 1 second. And then we did some calculations with that. Do you remember that? There was a prism with a rainbow coming out of it. Yes?
I have to go make a copy.
Okay. Yep.
Thank you.
So
Alright, bye.
scientists during the 1700s, knew that light was a wave. They knew it was a wave. They all believed it was a wave. They were all in continuous spectrum, like one to the next. It was all the same. But there were a few problems that they encountered, and the first one here is that objects tend to glow when they're heated to really high temperatures. And I'm sure you guys have all seen a piece of metal that's been stuck in a fire, and the metal will start to turn red. And then it'll turn orange and yellow. And eventually, if we leave it in there long enough and the flame is hot enough, it'll turn white. Have we all seen something like that? So that was a problem, because that didn't make any sense to them. And if we think of light as a wave, that doesn't make any sense whatsoever. So that was the first thing. Second thing is that we have this stuff called atomic emission spectra and atomic absorption spectra. Scientists knew that this happened, but they didn't have a clue why. It didn't make sense to them because light is continuous. All right? And then finally, we have this weird phenomenon called the photoelectric effect. And I'll show you a picture of that setup, and we'll talk about how that worked. But it did not make any sense if light is continuous. It did not make any sense whatsoever. So that was a problem with light as a wave. These are 3 problems of light as a wave. Okay, I don't know what's next. Let's see. I guess we'll talk about each one of them individually. So here's the first one. And I have on here a picture of a piece of metal, 2 pieces of metal. They're the same metal. Which one's at a higher temperature?
The back one.
Which one?
The back one.
This one here?
Yeah.
How do we know that?
Brighter.
It's brighter? It's lighter, it's more yellow, right? Because as we add more heat, we see that these objects, they can start to change color. And they start with red, which, remember I told you red was the low energy portion of the visible spectrum? And they move their way up until we hit white light, which is at the end. It's like that purplish, whitish light that it gives off. So temperature is affecting this. The definition of temperature is the average kinetic energy of particles in a sample. So the average kinetic energy of the particles in this brighter sample is much higher. The average kinetic energy of these particles is much higher. Because this is so much higher, it doesn't make a whole lot of sense just because they're higher that they're going to be brighter. If we think of light as a wave. So someone important that was studying this in the 1900s is a gentleman named Max Planck. Now there is a Planck's Institute in Europe, I want to say it's in Germany, where people study physics and chemistry because he made so many important contributions. And I'm going to tell you that Max Planck is responsible for this. All right? He said that light is not absorbed and given off continuously. He said that light is absorbed and given off in packets, just like little chunks of energy. And he called these chunks quanta. A chunk is a quantum. More than one chunk, the plural, is quanta. All right? So he said light's not continuous all the time. He said that light is given off in these chunks, and those chunks he referred to as quanta. The singular form is quantum. Okay? That created a problem because light has always been considered a wave up until this time. But now he's saying that light is not continuous. It's given off in chunks. So a lot of scientists did not like that. They did not believe it. They did not accept it. It was made people very, very uncomfortable. Now the other thing that he said is that very specific wavelengths of light are given off while these chunks are being given off. So let me explain that for a moment, because I can, I should have gotten my lasers out, my little laser pointers, that I can tell you that light has a very specific wavelength. One wavelength of light is a very specific color. Of course, I'd have to know where they're at over there. Okay. So on my laser pointer here, this is a green one, this is the blue one. It will say on my laser pointers that they are a specific wavelength of light. Let me get a battery real quick.
Why doesn't that battery work?
Okay, so I showed you a continuous spectrum of light when we talked about light as a wave. But each wavelength between 400 nanometers and 700 nanometers corresponds to a very specific color of light. That battery does not work right now. And those colors are very specific and unique based on the wavelength. Still does not want to work. This particular laser pointer has a wavelength listed on it. Read that. Your eyes are younger than mine. What's the wavelength?
Is it the 5MW?
No, that's the milliwatts.
Oh, 532 nanometers.
Ooh, that's weird. Aren't those the kind of numbers that we've been working with? What was it again?
532.
532 nanometers. Every single time that we see 532 nanometers, that is going to be this specific wavelength of light. I think I got that in there. See if I can work the laser pointer. You gotta be smarter than laser pointer. There it is. That specific wavelength of light is green. But that's specific green. If we go to, I already forgot what it is, 533 nanometers, the green will be slightly different. It won't be perceptible to our eyes, but a machine will be able to tell us specifically what the wavelength is. That's why when we look at the continuous spectrum, we see that one color blends into the other. We don't typically talk about green light. We talk about a specific wavelength of light.
So is there like an app or something where you can like type in a wavelength, like any number, and it'll show you what color it would be? Like, is that a thing?
Oh, I would imagine.
That's cool.
And if not, that's my idea. I want to make millions because everybody wants to know, right?
Yeah.
I feel like we're getting closer and closer to the lab we did yesterday. So this one is 405 nanometers. Actually, it's marketed as a blue laser.
It's purple.
It looks really magnificent.
Yeah.
It's, the color is pretty intense, right?
Like it,
Yeah, like looking at it makes our eyes go over the phone.
it's like my eyes can't
It looks
register.
blurry. Yeah, it's like it's not even a dot, it's like.
Yeah, so this is right on the edge of what most humans can see, can perceive. Isn't that weird?
Do it again.
It's tricky.
It's just like, it's really weird.
Can you kind of see shades of white light in that?
Yeah.
Yeah.
Almost like a black light? Because that's right on that edge. Now, the whole point in demonstrating that is that light, we don't really refer to light, specific colors, we don't refer to colors, we refer to wavelengths of color. And we know that 400 nanometers is on the blue or purple end, because this is 405. And we know that on the 700 end, that's where you're gonna have all the reds. So when Max Planck was working with this stuff, what he noticed was that these metals gave off very specific wavelengths of light, right? And then that's what we just talked about. This one is going to be more towards what we would refer to as the yellow region, and this one is going to be on the red-orange sort of boundary. So the wavelengths are going to be closer to 700 for this one, and probably closer to about 600, 550 for this one. So they're not giving off just colors of light, they're giving off very specific wavelengths of light. And that made people very uncomfortable because light is supposed to be continuous. We've thought of it for all these years, we, as in before 1900, they thought of it all those years as being a continuous spectrum. So for these things to only give off very specific wavelengths made everybody very uncomfortable. There was a divide in the physics community when it came time to discuss this because it made them very uncomfortable, so they just thought, we just won't talk about it, and then it doesn't exist. I'm sure you guys never experienced that. Ever. Okay, good. So he identified these quanta, and he said substances can only absorb multiples of whole quanta. That sounded gross, right? He said that materials can only absorb and give off multiples, whole multiples of these quanta. All that means is it had to be 1 or 7. It couldn't be 0.5. It couldn't be 5.3. It had to be a whole number of quanta that they either absorbed or they released. And again, he had scientific evidence to support that. But it made people super uncomfortable because that was a huge dramatic change from what they've always believed. This was happening in the at the beginning of the 20th century. We're not talking about something that happened 2,000 years ago. That was the time of Aristotle. We're talking about something that happened just over 100 years ago. New discoveries that were happening over just 100 years ago that we didn't know before. this is all coming about because of better technology to make these measurements and, more standardized equipment, right? So that's Max Planck. And I absolutely recognize that that's still kind of like, it's on the edge of, I get it and I don't get it all at the same time. It's okay. This stuff is heavy, we're gonna have to go through it a couple of times. Not like heavy, more massive, but heavy, like, requires a lot of thinking. That's okay. We're gonna go over it multiple times. We'll need to. But here, this is what you need to know. Well, you need to know all that stuff, but you need to know this as well. Max Planck, from his data, was able to calculate how much energy was contained in a quantum. After he said that, substances can only absorb or release whole quanta, he was able to take that information and calculate the energy of a quantum. But it is dependent on frequency, because remember, it's only giving off or absorbing very specific wavelengths of light. And we know that there's a relationship between wavelength and frequency because of the calculations that you were just recently doing. So this equation is Max Planck's huge contribution. There's so much behind that equation, but that equation is sort of what sticks around. Now, Kara, that's the equation you used from the Khan Academy videos. But this equation allows us to calculate the energy required, or the energy contained in a quantum.
Is that supposed to be the current V?
Yeah, this is the Greek letter nu. This is the sort of like the cursive version of it. H, usually H has a bar through it, like this. It's a terrible marker. That's Planck's constant. So I would like for you to get your packets out, please. Please turn to the back of the second page. Please turn to the back of the second page. So you highlighted, some of you highlighted, C, the speed of light in a vacuum. Do you see that? It's in that first box right there. It's the last one listed. Do you see the first one listed as H? That little bar across it? That is Planck's constant. That's what this H is. You might want to highlight that one as well. The first one, yep. Okay? That is Planck's constant. Now, all of my answer keys, and I do have the one I promised you, it's up here in pink. All of my answer keys use a different Planck's constant. But it's not different, it's just, it's 6.626 instead of 6.63. So it's not a different number, it's just,
So should we change that?
it's up to you if you want to change it.
What did you say the number was?
6.626. The exponent stays the same, but it's just a little bit more detailed, more specific, I guess. A finer measurement, yes.
Would you rather us use 6.26?
It's up to you. I don't really care which one you use. It's just going to be important that you indicate which one you use, and you will do that as you show your work. That's all.
You say it's fine.
Yes, 6.626. Yes.
In the equation on the board, the B-looking thing, would that be the frequency?
That is the frequency, yes. That is the frequency. And if you look in the box right below it, it has, the first equation listed there is the one that's up here on this board. Now, I'm not gonna go through it. If you really wanna see it, I will go through it with you individually, but the second equation listed here is the same exact equation, except it uses wavelength instead of frequency. So this is just combined with the equation that you did use for those homework problems. And now you have an equation to calculate the energy based only on the wavelength. All right, that one's based only on the frequency. You have the second one here is based only on the wavelength. So if you would want to highlight those or put a box around those, then that's absolutely fine. But those two equations are going to be useful in calculating the energy of a quantum. You have other problems on this worksheet that you now can do, because those are energy problems. I'm not gonna give you an assignment today, but I probably will here in the near future. And the other paper, the one that I gave you first with the table on it, now you can do all of those as well, just based on the equation that we were using and this new equation, you can do all those problems as well. Yes?
What equations did you say we might wanna highlight? Is it the
The first two listed in that second box.
other equation?
Mm-hmm. Any other questions before we go on? Okay, so, let's go on to the next piece of the story, because again, this is all happening sort of at the same time, and some of this stuff is feeding in, and we don't see a connection yet, we're not going to see a connection yet, and that's what confuses students the most, I think. But those look familiar, don't they?
No, like that.
You don't like that?
No,
Why not?
because I'm so confused.
Are you suggesting that perhaps what we're looking at now is what you guys might have seen yesterday by looking through those spectroscopes? What? I hate it when that happens. I wish I would have planned it. Okay. So, this is the second problem with light as a continuous spectrum. So what I have up here, I have the visible spectrum only, right? We know that infrared is down here and communication waves are all the way at the end, and then up here we have ultraviolet and we have gamma rays all the way at that end. But we're only looking at the visible portion. Here's our continuous spectrum. Everything bleeds into everything else. So scientists have been looking up at the stars ever since, I don't know, the 1500s, the 1400s, whenever Galileo lived. And you know, after the invention of the telescope and then Galileo started looking at the sun, he eventually went blind from that. But after scientists started looking at the stars, they were able to identify different spectra. These are spectra that the stars either gave off or that they absorbed. All right? So I'm just going to point out the difference here between these two. This is an atomic emission spectrum. What does it mean to emit? To give off. So this is light that has been given off. We have a hot gas. Whatever energy is coming out of that hot gas, let's say a star, if we separate it through a prism or one of those spectroscopes that you guys used yesterday, what we observe is the light or the radiation that was emitted. That's an emission spectrum. But sometimes the heat source is behind a gas. So this light bulb here, that's our heat source. That's energy, and that energy is going through the gas, and that gas is absorbing some of the energy. It's taking it out. And what's left over gets passed right through, and we separate it using a prism or one of those spectroscopes that you guys used yesterday, and then we see the atomic absorption spectrum. If this is the same substance, we will get spectra that when we put them together, when we add these two back together, what do you get? The continuous spectrum. So, here's what's happening. When energy is being given off by something that's hot, and we've all felt radiation from a fire, right? Whether you have a bonfire, you have a fire in the fireplace, you can feel that heat energy coming out of there. When we have something that's hot and it's giving off that energy, what we see are just the pieces of energy that are given off. The portions that are in the visible spectrum are these very specific wavelengths of light. But if we have, I don't know, something really hot and it's going to pass through something that's not as hot, energy is going to transfer to that thing that's not as hot, and it's going to pull out only certain amounts of that energy. And in this case, it's pulling out those very same, very specific wavelengths of light. So if we would put those two things back together, we get the continuous spectrum. That is evidence that a substance only absorbs very specific frequencies of light or wavelengths of light. Substances only absorb very specific wavelengths of light. That's kind of a throwback to what Max Planck was saying, right? Because only certain substances will glow certain colors. They give off very specific wavelengths of light. Scientists knew this for a long time, but they couldn't put the pieces together to explain why it was happening. And a lot of scientists still didn't want to touch it because it made them very uncomfortable to think that light was something other than this wave that gives us the continuous spectrum. So I have to talk about ground state and excited state here because what's happening is when we heat something up to a really high temperature, we take the materials, the substances that make that up, the molecules or the atoms, and we raise them to something called the excited state. And the excited state is just where the atom or the molecule contains more energy than it normally does. More energy than it normally does. That's an excited state. When it has just the normal amount of energy that it always has, it's at its ground state. Sort of like you guys right now are in the basement state. You don't want to interact with me. You don't think I'm funny. A little hurtful, but whatever. When you leave my room, you'll be in the excited state because chemistry's over for the day. And then eventually you'll settle back down into the ground state where you're just, yourself. Does that help explain it?
Because you said excited state contains more energy than it normally does,
Mhm.
and then ground state is like.
Just this normal, everyday amount of energy. Okay? So when we heat something up, it's excited. When we let it cool down to room temperature or space temperature or wherever it happens to be, then it's in its ground state. And those have very different behaviors. Okay, not very different, but they have, they do different things. I think that's a better way to say that. And the answer key was on the wall the whole time yesterday. See over there? Between the shower and the pencil sharpener? Those are all atomic emission spectra for most of the gases we looked at yesterday. And then it's got some for the stars and other stuff like chlorophyll. No? Not excited? All right, let me see if there's anything else I need to tell you. Nah. All right, let's move on. All right, so the photoelectric effect. What time is this class over? Oh, we have plenty of time. All right, the photoelectric effect. I really have no idea why this was even a thing. Not a clue. I probably should look into that at some point. But scientists knew this happened. So what they would do, they would take a metal plate and they'd curve it. So that's the metal plate that's curved around. And then they would take a metal post, like this, and they would put it inside of this glass, it's called a bell jar. It's literally just a glass dome that goes over the whole thing, and they can evacuate that bell jar. So they apply a vacuum to it, not a vacuum cleaner, like a vacuum pump, and it pulls out all the matter that's contained within there that might be some gas. So air, oxygen, nitrogen, whatever, they can take that all out of there. And then what's left behind is just this metal plate and this metal post. Those are interchangeable. So you can see that this might be copper and this one might be silver. They can change those out. Could be, next time they change it out, they might make this metal plate gold and the metal tube zinc. It doesn't matter, right? So they can change those out. They're interchangeable. And then they plug this in and they attach a power source to one end and they attach a meter to the other end, and they look for current to flow. So, and this is an analog meter, so it's one of those where the needle jumps around. Again, I have no idea why they would do something like this, but what they notice is, I mean, these pieces of metal aren't touching, so is this thing gonna register any current at all? No, it's like when we flip the light switch off, the circuit is open and no electricity flows. But when we flip that switch back on, it causes the two pieces of metal to touch and the circuit is closed so electricity can flow. Here, the circuit is always broken because these two, this metal post and this metal plate, they're not touching each other. Well, they can get electricity to flow in this. It's the weirdest thing. But it requires a certain frequency of light in order for it to happen. Yeah. So what they do is they take a very specific kind of light, let's say a blue laser, and they shine this blue laser on that metal plate, and that metal plate, I don't know, does something. And if they do that, even when they first turn that laser on, I know it hurts your eyes, I apologize. Even when they first turn that light on, electricity flows through this thing. That makes absolutely no sense if we're talking about light as a wave. And it only happens with certain frequencies. So maybe the blue laser works, but the green one doesn't. White light doesn't do it. Otherwise, we'd have electricity flowing all over the place all the time. And you'd get shocked by everything. So that doesn't work. So there's something about that very specific frequency that we can tune in. And I use frequency and wavelength interchangeably because we know how to switch between them using the speed of light in a vacuum. But, I mean, they could not explain why this was happening for a ton of time. A ton of time. And now I'm going to tell you why it happens. And first I'm going to tell you who did it. Who do you think did it? Albert Stinkin' Einstein. Okay, so a little bit about Einstein, because you know he's got an interesting set of hair.
Who did that?
No, he explained it. Scientists did this for a long time. They had no idea why it worked. They just knew it worked. But Albert Einstein was the first person to explain it. So Albert Einstein, he could do math. He just didn't like to do math. He wasn't as strong in math as he was in other things. He used a lot of people to help him out with his math. But he had gone to school, so he graduated from what we would consider high school, and then he went to university. Nobody wanted to take him on as a grad student. One, probably because he was an incredible jerk. But two, because he just, you know, he always challenged everybody, all right? He was arrogant, that's what I mean by a jerk. He was arrogant and he challenged everybody. So eventually he found somebody to take him on as a grad student so he could get his PhD and he could teach at the university level. But in between all that, when he couldn't find a job, he was working in the patent office. So, you know, people were filing patents and he would have to go through and verify that nothing had been done with that before. And then, you know, if they did, then he would have to call them back in and say, no, we can't give you a patent because people have done this before, blah, blah, blah. You know, really boring job, well below his skill level, you know. Anyway, so he's trying to keep up on all this physics stuff because he wants to be teaching physics. That's what his goal is. And he actually came across a paper that was written about the photoelectric effect, and he was like, I don't know why people can't explain this. Here was his answer. Light's not just a wave. Light can act like a particle. There you go, summed up, the photoelectric effect. Light acts like a particle. So let me explain to you what's happening here. It's actually the electrons that are responsible for electricity to flow. Charged particles, so electrons. Here's what Einstein says. Inside of that piece of metal, there are electrons. They're more mobile. Remember we talked about metallic bonding? The electrons are more mobile. They can move around in that piece of metal. So if we shine some light on that, and that light comes in packets of energy, right, Max Planck's quanta, if we have a quantum of energy and we give it to that electron, it might be enough energy to cause the electron to be ejected. What does it mean to be ejected? Kicked out. That electron gets kicked out of the metal plate. Well, where does it go? Jumps to the metal host. Well, if we have an electron jump from the cathode to the anode, that's what we call electricity. So if we continuously shine a very specific frequency of light on this metal plate, it's constantly kicking out electrons. And they're constantly jumping from one piece of metal to the other piece of metal. They're completing the circuit. So let's think about this in like realistic terms. Let's say that I am an amazing softball pitcher. And I carry around my softball, and if I see you make a face at me or blink, I'm gonna throw the softball at you. Well, if I'm an amazing pitcher, how fast is that softball gonna be moving? Really fast. Do you think it'd be fast enough to knock you out of your chair if I caught you off guard? That's what's happening with the electron. But let's say Mrs. Hess comes over here and she is not very good. She barely can hold the ball. And she just kind of like tosses it to you. Even if it catches you off guard, is that enough to knock you out of your chair? Didn't have enough energy, right? So the amount of energy that that light contains is important. And that amount of energy is connected to the frequency of the light. So if it has sufficient energy, it can kick the electron out. That electron can jump from one place to the other and complete the circuit. If it doesn't have enough energy, then nothing's going to change. You're not going to see electricity flow. Albert Einstein explained all that after years of people not being able to explain that. And he won the Nobel Prize? Not for that. He wrote 3 groundbreaking papers that year. One was on the photoelectric effect. He won his PhD for Brownian motion, which is about the dumbest thing ever, but that's beside the point. He rubbed people the wrong way, as most geniuses do. So, it was that sort of explanation of the photoelectric effect that unlocked a new model for the atom. Let's see what's next. I have to flip the page. So let's stop here with notes. We're not done yet. So, how does all of this connect with what you guys did yesterday? It is what you did yesterday?
Like the different levels of frequency, light frequency.
Yeah. So, remember how, ooh, you all right? Yes. Remember how, when you looked in that spectroscope, you had to line up the light with the slit, but if you looked to the other side, there was a scale in there? So that scale allows us to measure the distance between those.
Were we supposed to, we were
Bands?
supposed to look at the left, right?
You kind of have to look all over, because it just depends on your eyes where it appeared.
Okay.
So, when you looked in there, you saw a scale in there, we could actually calculate the wavelength of those bands. But you guys didn't really know what you were looking for yet, so, I mean, it was just fun to watch you guys figure that out. Was that an easy thing to do?
No.
And if you didn't know what you were looking for, that made it even worse, right? Now, if we had had this discussion and I had you do that today or tomorrow, would it have been easier? Would you have known what to look for?
Yes.
Do you think the scientists that were working on this stuff, do you think they had any idea what was going on?
Probably more. They're a little bit smarter, maybe.
They can make connections, but I want you to think about right now, in this world, we have Rutherford's model, which has the nucleus in the center with protons actually, in the 1900s, we might not have the nucleus yet. Some of this stuff was being done before we knew the structure, Rutherford's model of the atom. We had no idea the neutrons existed, because that didn't happen until 1932, and all of this stuff was happening before that. So if we did have Rutherford's model, we have the positively charged nucleus in the center, and the electrons are somewhere outside of it. That's what they have to work with. We know a lot more today. You guys are going to learn a lot more in the next week or so. But they didn't have any idea. They just were trying to take these pieces and put them together like a puzzle so that they could see the complete picture. What about the discs? What do you think was the purpose of them?
Oh, no.
You don't know?
Yeah,
No? Could they look at an atom?
They did like,
Get their magnifying glass and hold still, look really closely at it? Is that, could they do that? So they're taking evidence and making predictions. That's weird. I feel like that's what you guys do. You collected some evidence?
Oh, it's a lot.
I don't know, whatever's on the
Are you
inside.
talking about the discs?
Uh-huh.
Yeah.
And did you make predictions based on the data that you collected?
Attempted.
You attempted to? Well, I mean, that's what they did too. Like, we had Democritus's, John Dalton that have the same model of the atom. And then we had J.J. Thomson's model, and we have Ernest Rutherford's model. And we're gonna see another model before we even see the real model. They all just took what they could get and put that together to give them a new picture of what they thought it was.
Does it sound like a good plan?
Hmm?
Does it sound like a good plan?
Well, these people, that was their life. They really loved their science. Just like you guys do, right?
life is so crazy. Like everything's a prediction.
It is. It is. And, you know, that's starting to border on philosophy, which is, it's too, I don't like that, because it's too, like, analytical on how we view the world and what that really means. Are we constructing all this? Like, am I constructing all this in my head? Because if I am, that's even more disturbing than the squirrels that are always running around up there, right? Anyway, yes, Sarah.
Okay, think of this. What if they weren't actually wrong about their models, the atom was just constantly changing?
That is a good point. What do you think about that?
I don't know, I don't know.
I mean, we do refer to it as the evolution of the atomic model. So who knows what the next stage will be? And maybe, to even sort of piggyback on that, what if the better technology that we can develop gives us a better picture of what the actual model is as it is evolving? And is our better technology causing it to evolve? That's so weird. Yeah. Stupid philosophy. Worst class I ever took in college. It was awful. It was awful. But I was on quarters, so I only had to take 10 weeks of it. You guys are gonna be all on semesters now, so sorry. So we don't even have a true model of the atom yet. So you still can't answer that last question. But I hope you can start to see how some of what we did discuss today is starting to, I hope you're starting to put that information together to start answering that question. Now, I need to kind of have an idea of where we're at. So a lot of information today, and it's all very, like, I don't know, it's almost like just out of reach. Am I on the right track?
I feel like I don't know what applying it will look like. Like I don't know what that's gonna look like.
Okay. Do you understand, did you understand little bits and pieces of what we discussed? Just having trouble putting it together, and as soon as you walk out of the room, it's gonna like jump way over to that corner and you can't reach it? Yeah, so that's exactly where I expect us to be. That's very typical of this stuff. Like I said, this is very complex, very abstract, very, without getting into too much math and science, like we're just sort of skimming the surface. Okay, so I will tell you that this is listed in my standards, so you have to be able to explain the photoelectric effect. And I also wanna tell you that it's really easy to fall into the trap of, well, Mrs. Foley just talked about this, but you don't have to just use me. Right? I mean, feel free to ask Mrs. Hash, she's probably gonna tell you, like, I know, I've heard of it, but I don't know what it is. But Khan Academy is a great place to go, and it's verified information. Other places, there's the Organic Tutor, I don't know if they would talk about the photoelectric effect, but that's another very stable, reliable source. But I would search online. Sometimes they can explain things in a different way, and that helps. So the photoelectric effect is something that you will see on your test, you have to be able to explain it. And I'm not talking about a test yet, like the date's not up there. But I'm just pointing that out now because we just talked about it. The atomic emission spectra and the, did I call them black bodies? No, probably not. The glowing metals, those, I am not going to test you over the glowing metals for sure. There might be a question about atomic emission spectrum just because we did a lab about it. I'm sorry. We'll see.
What do we have to explain about that? Like the light is a particle, like that part, or
Just sort of like, this has historical significance.
an overview of like
So,
what happened in
yes.
the, so basically like how they put like one metal rod and then the metal sheet and like how
What's
light
happening.
jumped or electricity was created.
Yes, what's happening and why it only happens with certain frequencies.